We begin a new topic that is related to Bayesian methods. And before we will begin discussing Bayesian methods, I have to tell you a little bit about statistical modeling and related problems. So, Bayesian methods. So probably today's lessons will be a bit more theoretical, and on the next week we will discuss more applications and actually more Bayesian methods. But I will begin with a more classical thing. This is called maximum likelihood estimates. And I want to reiterate some things that we already discussed and put them into some more general perspective. Actually, this is very universal way to answer some statistical questions. And first of all, if we have some problem, we want to analyze some data and give some answers, we have to model this data as a result of some generation by some statistical model, by some probabilistic model. What is probabilistic models? Basically, we have some random variables, and we believe that our data are obtained as a realization, usually independent realization of these random variables. For example, I provide several examples. First example, we have something like a coin tossing. For example, we can think about choice of one of two possible forms of a particular word. Assume that we have a word, and this word can be in two possible forms. For example, it can be in dialectical form and in normative form. And we believe that when a particular person produce this word, they just use something like a coin tossing. They toss a coin and choose which word to use according to the result of this coin tossing. This is a very simple model, but it is really often used in different contexts and with additional complications. But anyway, this coin tossing model is what we have in our mind when we discuss this kind of modeling. So we can believe that, for example, this choice is done by coin tossing. So choice. Of course, it doesn't mean that probability of getting dialect word is the same as probability to get normative word. So this coin does not necessarily have to be fair. So this is a coin that have associated probability P. For example, it is probability of getting dialect word. Then we have some data. Possibly this data looks like we can start with some text. And in this text, we have this word sometimes that can be in either of two forms. So this is our word. And every time we see this word, we can create just a record that will be either 0 or 1. For example, we can encode 0 normative, 1 dialectal. So in this case, our data will be transferred to this series of zeros and ones. And we believe that these zeros and ones are result of this coin tossing. So this is a model. Of course, we understand that people do not choose which word to use by coin tossing. Of course, this is just a huge simplification of what is going on in the real life. But we have to use these models to think about them in a probabilistic way, and to be able to use statistics and to use probability theory to get some quantitative answers. So let us rewrite it once again in more strict terms. So we believe that our sample, so formally, we believe that we have sample x1, x2, and so on, xn. And each xi is, do you know how this random variable is called? If it can take values zeros and ones, and it takes value 1 with probability p. Do you know how to call this random variable? Do you know the name of this distribution?
Binomial? Binomial?
Binomial distribution, yes, it is. Actually, this is an extreme case of binomial distribution with its own name. This is called Bernoulli random variable with probability p. So xi takes value 1 with probability p and 0 with probability 1 minus p. So this is called Bernoulli random variable. And sometimes we are interested in the sum of these values. So for example, x capital, let it be just a sum of these values. What can you say about distribution of x capital? So we believe that these values are independent. So what can you say about this value of x capital? What is
it is also a random variable.
Hmm?
It is also a random variable.
Yes. What can you say about its distribution? Again, it have its own name. Basically, this name was already mentioned.
Binomial now.
Yes, this is actually binomial, yes. This is binomial with parameters n and p. So n is number of coin tossings, or sometimes people say number of trials. And p is usually called probability of success. So this is very this is just a name that it is success. Just this is arbitrary choice what call success, but in this case we just say that if you have one, if we have a dialectal form, then it is success. So if we have n trials and probability of success in one trial is p, then the number of successes in these trials is distributed according to this binomial distribution. What usually happens next? When we have this model, we usually have a problem of estimation of parameters of this model. We usually don't know some of the parameters of our models, and we want to estimate these parameters from the data. For example, if we are speaking about this part, which parameters of this binomial variable is unknown, most probably. Which parameter is usually unknown?
Probability.
So if
Probability.
yes, this p. Actually, this distribution depends on both number of tossings and probability of success, but usually we know number of tossings because it is just number of our values in our sample. But we usually don't know this probability of success. So we have a very generic problem. We have data. We believe that this data is generated from our model, and we want to estimate parameters of the model. So basically it means that we return here to the problem that we discussed at the very beginning of our course, that we have a coin, we toss this coin, for example, 5 times, we get 3 heads, 3 ones. What is the probability to get one? What is the value of p? So these kind of problems are stated in this way. But actually, these kind of models can be much more complicated than the one that I have here. Let me introduce another possible problem. Let us assume that I have some numeric values. I have x, and I have some numeric values. Like this. And I have x1 and so on xn. Now they are not zeros and ones, but they are just some numeric values. And we have a model that these values came from some normal distribution. Normal distribution with some expected value and with some variance. So it means that we believe that there exists some random variable for which we have normal distribution. So we have some random variable with some density. And this density is given by this normal law. So we have mu here, and we have sigma squared, which or sigma, which gives us the variance of this model. And we believe that our points are produced by running this random variable, by sampling from this random variable. It means like that we believe that there exists some computer, and this computer generated numbers by invoking of a function like get me random number from this distribution. And again, it is possible that we are interested in parameters of this distribution. So we have some numeric values, and we are interested in parameters of this distribution. We want to estimate mu and sigma squared. So this is another possible problem for which we can which can arise from these models. Let us discuss how can we estimate these parameters from some abstract model. Let us return to this example, simple example with binomial model. That my data looks like something like this. What can you say about P?
P is equal to 1 or to 0.5.
So you believe that it equals to 0.5. 1, 2, 3, 4.
Oh, no, I don't. 1, 2, 3, 4, 5, 6. 6 to 10. So 0.6.
Okay, so you definitely believe that P equals to this value. And it is not possible to get any other values of P.
Well, the value can be different if we have more trials.
Yes, but what I'm asking for is I'm asking about this unknown perfect value of P, not about some property of your data. I don't ask now the value. I don't ask now the relative frequency of these ones. I ask you about this value of p. So you say that p equals to 0.6. What can we say about this answer? Is it true that this answer, well, is it possible that actual p equals to 1/2, contrary to what you say?
Yes, it is possible.
It is possible, but can you say that value 0.6 is better than value 1/2 by looking at this data?
Yes, we can.
Why?
Because this value of p can predict our real data better.
Yes, basically, on one hand, we can say something like this. We can say that, okay, it is possible that this data is produced just by fair coin, the coin that gives you ones and zeros with equal probabilities. But if we are asking about the value of p such that our model, in a sense, best fit to this data, then you can say that this value is better than value 0.5. Actually, we can create a correct way to think about it, and this is actually maximum likelihood estimates. And to do it, we have to introduce likelihood. So likelihood. Likelihood is a function of parameters of my model. In this case, it is p. And this is a probability to get the data we actually observed for given value of p. In this case, let us assume that our data looks like this. Then we can define this likelihood of p. This is some particular function. We can find it just by writing down the corresponding formula. Let us do it. So you can recall classes with Nina Sakharova about probability theory and about binomial distribution. And please find likelihood function for our data. So I will give you a couple of minutes to do it. I want you to write down some formula. And in this formula, you have to include this p because it depends on p. Actually, of course, we are not interested in the order of these values. So we can compress our data and consider not this sequence of zeros and ones, but okay. I think we can think about these zeros and ones. Probably it is even easier. So I want this likelihood function for our particular sequence of zeros and ones. So we believe that these zeros and ones are created as independent realization of some Bernoullian random variable. So every number here is just a result of coin tossing. So I want you to find likelihood for this data. So this is a function of P. When you're ready, please send your formula to as a private message in chat to me. Just a second, I will return my screen. So, are there any answers? I want your answers in my private messages. Or you can, as an alternative, you can ask me questions about this part of the lecture. So I have two answers in my private messages so far. One is partially correct. So if this question is difficult, let me ask you another question. For example, assume that P equals to 1/3. What can you say about what is the probability to get our data. If you can answer this question, then you can just replace in your calculations number 1/3 to arbitrary number p and get the correct answer to this question. Okay, so I have a first correct answer in my private messages, but I need more. I really want you to understand this stuff. This stuff is not mathematically complex in the sense that you don't have some huge calculations here, but it is very important to understand answer to this question. Otherwise, we cannot proceed. So just please do it. Now that we believe that all these numbers, this number and this number and this number, we believe that they all are independent with each other. And we can use it in our calculations. So if you cannot answer this question, just ask me some questions about this problem. So probably let me decompose it a bit more. What is probability that x1 equals to 0 for given value of p? then you can answer another question. What is probability that x1 equals to 0 and at the same time x2 equals to 0 given for given p? The next question is what is the probability that x1 equals to 0 and x2 equals to 0 and x3 equals to 1 for given p? This formula is not exactly a conditional probability. So I use this vertical bar just to say that we have this thing as a parameter. So we are interested in this event, provided that we have some particular value of this parameter p. Okay, probably we can continue. So So let us consider this set of values. We believe that each value was generated as independent realization of a random variable that takes value 1 with probability p and value 0 with probability 1 minus p. So note that in our case, p is just an arbitrary value. So here we discussed what is more or less probably value for p. But here after this line, p is just some value that we don't know in advance. This is just some arbitrary value, arbitrary number from 0 to 1. And now I want to answer. I want to answer this question. I want to find this likelihood. It means that if I know that probability of getting 1 equals to p, what is probability to get 0 at the first place? If we have only zeros and ones, then if we have this 0, then probability to get 0 is equal to what? What should I write here? You can answer just by voice.
0.7?
No. Look, this thing depends on p. This thing depends on p. So if probability, yes, exactly. If probability to get 1 equals to p, then what is the probability to get 0 here? It is 1 minus p. And now what about this case? Now I ask you, what is the probability that x1 equals to 0 and x2 equals to 0? So if we have 0 here and 0 here, what can you say about this probability?
1 minus p squared?
Yes, exactly. This is due to independence. We know that if we have independent random variables, then the corresponding probabilities can be multiplied. If we find probability of event that this happens and this happens, then you have to find probability of this event, and multiply them. This is due to this independence. So we have this 1 minus p times 1 minus p, and the result is 1 minus p squared. So the third example.
1 minus p squared times p.
Exactly. We have two zeros that corresponds to this 1 minus p squared, and we have one value 1 that corresponds to this p. So we multiply 1 minus p, and p, and we get this value. Now, what about our initial sequence?
1 minus p fourth degree. I don't know.
Раз, два, три, четыре. Yeah, to the fourth degree.
Yep, and p to the 6th degree.
Correct. This is our likelihood. So actually, the important part of this exercise is to understand what likelihood is. Likelihood is a function of our parameter that gives us probability to get our data for this particular value of this parameter, like in this formula. So,
Well,
yes?
may I ask a question?
Sure.
The formula is quite easy if we work with binomial stuff, but what if our variable is more difficult, is more complicated than just binomial? How do we count likelihood then?
Well, sometimes we have just exact formulas for these likelihoods. Sometimes we have to use some algorithms that allows us to do it in some implicit way. But actually, if you construct your model using well-known random variables like binomial, normal, Poisson, and so on, you know distribution of all these variables, and then you can do you can find likelihoods just like we did it in this exercise. Actually, we used two main considerations. First consideration, we know if we know p, then we know distribution of a particular value in this data set. So if we know p, we know how x1 is distributed. And then if we see a particular value here, then we can find probability of observing this value. It is some function of p. So this is our first question. And the second part was that for different values, we can multiply the corresponding probabilities. This is due to independence.
And what if it's dependent? What to do if the variables are dependent, not independent, but dependent, like letters in the word, for example, or words in the sentence?
Well, then you have to consider more complicated models like Markov chains or something like this. They take into account these dependencies. So your model becomes more complicated. But in most of cases in statistics, people work with data that is believed to be, so your one observation is believed to be independent of another observation. This is a general assumption of basic statistical models. Of course, sometimes it is violated. Sometimes people ignore these violations. Sometimes people consider a more complicated model. I think that if you have something like words in a sentence, the easiest way is to model it as a kind of Markov chain. But I'm not sure that we will be able to discuss Markov chains in this course because we have only one lecture so far. But if you want, you can just, if you have some problem, you can just let me know and we will discuss it. I will tell you everything about Markov chains that you need. So now we assume that everything, that particular observations are independent. So now we have this likelihood function. And what does it mean? We can consider this likelihood function as a way to measure how good our data and a particular value P, that is a parameter of our model, how good are they in agreement or not? How good they are aligned to each other? And then we have the following idea. Let me draw a graph of this function. Okay, I can just use a software that will draw me it. I have GeoGebra. So we have 1 minus x to the power 4 times x to the power 6. Oops. Not very stable. Okay, I want to see it only on this segment from 1 to 0. So let me try again. Hmm. So we have this graph, and what can you say from this graph? For example, what is the probability to obtain our data provided that p equals to 0?
It's 0?
It's 0. Yes. So if we know that we have a coin that never gives us ones, we just cannot get our data. And the same holds for another point when we have p equals to 1. But in between, we have some positive probability. For example, if we have some value like p equals to 0.2, then we have some non-zero probability to get our data. But you also see from this graph that we have some point for which this likelihood is the maximum. What is the corresponding point?
0.6?
Yes, correct. 0.6, this value. And so we can ask ourselves, if I want to choose the value of my parameter p that fits such that the data fits this parameter p to the highest extent. So what is the best possible value of p? Then you can say we understand that we have these probabilities. We understand that it is possible for value 0.4, it is possible to get the data that I have. And for value 0.3, it is also possible to get the data that we have. But for value 0.6, we have our likelihood is the largest. It is the point of maximum. And so if I have to choose, well, I understand that I don't know the correct value of P in any case. If I have just this data, then I can just try to provide a good guess for my value of P. I do not know the exact value of P. But if I have to point just one value of P, then I would use value 0.6, because this value gives me the largest probability of obtaining my data. So if I draw this graph and I get point 0.6 here, and my graph looks like this. And then I can say that if P equals 0.6 is maximum, okay, it maximizes likelihood. And then we can say that P equals to 0.6 is maximum likelihood estimate. For parameter. Okay, let me put some head here. For parameter P for our data. This is, in fact, in agreement with our initial guess. But note that we used a different way to find this value. Here, you just calculated the number of ones and divided to overall number of values. But here we created a much more elaborate procedure, and this procedure provided us the same answer. But this procedure is much more universal. It allows one to estimate parameters of the model for a given data, and this estimate is in a sense good. I don't want to explain in details what does it mean good, but let me just mention one property, that if amount of data tends to infinity, P hat tend to actual P, correct P. And this is actually a universal property of this kind of estimates. So if you have some model and you have some parameters of this model, and you're trying to estimate the values of these parameters using data, using this maximum likelihood technique, maximum likelihood algorithm, then you can be sure that if you have a large amount of data, then your estimation will be good. At least in this sense, that they tend to the value of P, the correct value of our parameter. So I want to solve a couple of other problems that are devoted to this notion of likelihood and maximum likelihood estimates. Let me introduce another problem. For example, assume that I have let x1 be normally distributed random variable with parameters mu and 1. Okay. Before we will discuss normal distribution, let me consider a bit simpler example. Sorry for some mess. Let me consider some more simple example. Let us assume that we have value x1. Okay. I have some random variable x capital that is distributed according to the following law. It can take 3 values, 0, 1, and 2. And we have some parameter theta. And probability of taking value 0 is theta. Probability of taking value 1 is theta. And probability of taking value 2 is 1 minus 2 theta. So theta is some parameter. It is from 0 to 1/2. Let us assume that we have data that consists only of one observation, x1. And this x1 is taken from this model, from this random variable. What can you say about I have two. So let observed x1 is okay. Let me assume that I have two values, x1 and x2. They are both from x and are independent. And let us assume that observed values are the following: x1 equals to 0 and x2 equals to 2. Find first likelihood function for our data. And second, maximum likelihood estimate. For parameter theta. So I want you now to solve this problem. This is actually similar to the problem that we discussed previously, but instead of considering just series of Bernoulli random variables, we have a couple of random variables that are distributed according to this law. And I want you to find likelihood function for this data. And I want you to use this data to find maximum likelihood estimates for theta. So we can make a break and then continue after 10 minutes with discussing this problem. So we continue. Again, I want your answers to this problem in private messages. So this problem is very similar to the previous one. So we discussed the previous one, and we can just repeat the same steps in this problem. So I really expect that everybody will solve this problem, and I will get, well, how many users do we have? That I will get 12 correct answers in my private messages. So I'm waiting for your correct answers or incorrect answers, which is also good because we can discuss why they are not correct. Or I'm waiting for questions if you have them. So I have some answers. Some of them correct. And which is even better, I have some interesting questions. So we can probably continue. So we have two parts in this problem, and this is a usual thing when we do this maximum likelihood estimate. And first problem is to find likelihood function. And in this case, likelihood function is probability to get the data that we observed. For given value of parameters. In this case, parameter is theta. So the data that we have is this data. And so we have probability of the following event. x1 equals to 0 and x2 equals to 2 for a given parameter. And now again, we use two facts. First fact is that we know the distribution of x, and we know the distribution of both of these elements are the same as x. So we know the probability of this event, and we know the probability of this event. They are obtained just from this table. So we have something like a probability that x1 equals to 0. And we have probability that x2 equals to 2. And to find actual likelihood, we have to find probability of this event. And due to assumption of independence, we can just multiply these probabilities. And then we use this table to find this probability and this probability. And we see from this table that the first term is just theta, and the second term is just 1 minus 2 theta. And this is actually your answer for the first part. So this is my likelihood. Note that likelihood function is defined for a particular data. So for this data, we have one likelihood function. For another data, we will have a different likelihood function. So likelihood function is some thing that is defined by two entities, by your data and your model. And likelihood function, in a sense, shows you how good your data is corresponds to your model, or how good your model fit to the data, in a sense. So it depends on data. And this is an answer for the first question. Are there any questions? Mm-hmm. So what about the second question? Actually, in the second question, we don't have any mathematics, any probability theory, and we don't have any references to our data. All references to our data are already taken into account when we found this likelihood function. To answer second question, we just use some calculus to maximize this function. And actually, this particular function is very simple. And we can say that theta hat, maximum likelihood estimate for theta is just the value of which maximizes this function, theta 1 minus 2 theta. And then you can either use some derivatives, Or you can just take into account that, well, if I consider this thing, I see that this function is like this thing. So what kind of function it is? What is it? Is it linear function with respect to theta?
No, it's not.
No, it is not linear, but what kind of function?
It's a quadratic function.
It's a quadratic function, yeah. And we know that the graph of quadratic function is parabola. And actually, we can immediately find maximum of this parabola because we can figure out that we have two roots. If theta equals to 0, then the value of this function is 0. And if this bracket is 0, so if theta is 1/2, then this thing is 0, and this thing is 0. So we have 0 and 1/2. And then we have a parabola. And this parabola looks like the following thing. And parabola is symmetric. So its maximum is exactly in between of these 2 points. So it is 1/3. Sorry, not 1/3, but 1/4, 1/4.
But can you explain why do we calculate the maximum for this particular function we got in the first part of this task? I mean, if we got another, for example, x1 would be 0 and x2 would be also 0, we would have another likelihood function. And
Exactly.
then you said that we use these likelihood functions to see how well our model describes the data. Though, I mean, this was only one experiment. Why do we calculate the maximum for this particular one? Shouldn't we just try to make something more universal, I guess?
Well, we want to find some procedure that allows us to look at the data, look at the model, and find, in a sense, optimal parameters of the model that fits to this data. In this case, our data are very simple, just 2 observations. But this is just to simplicity of calculations. It is possible to consider, for example, a case when we have like 100 observations, 100 values of 0, 2, 1, and so on. But the strategy will be the same. So we say that we want to find theta that corresponds to this particular data.
Yeah, I got it.
So we see that for this data, maximum likelihood estimate for theta is 1/3, is 1/4. This is actually, well, this is actually quite natural, because if theta equals to 1/4, then, well, if theta equals to 1/4, then it means that this thing equals to 1/2, and we have something in between. So if we increase theta, then this event will become very unlikely. And if we decrease theta, this event will become very unlikely. So this is the optimal theta, in a sense. And okay, let us consider another example with the same x. Let us assume that now that our sample is just 0 and 0. Can you find MLE estimate for theta? No. So we have just two zeros.
1 divided by 2.
Yes. Yes. If we have just two zeros, then our likelihood is just theta squared. And then if we want to make this likelihood as large as possible, then we have to find as large theta as possible. So in our experiment, in our model, theta changes from 0 to 1/2. By the way, let us return to this table. Why theta cannot be larger than 1/2? Why we have these limits? Why it is not possible for theta to be larger than 1/2?
Because in this case, the probability of getting 2 would be less than 0.
Yes. Actually, this condition just follows from the condition that all probabilities should be non-negative. So in this case, if our sample is just 0 and 0, we have the following graph of likelihood, and then we have to make when to maximize theta, to maximize this likelihood, we have to take theta equals to 1/2. So we see that different data gives us different estimates for theta. And this is actually what we expect. Are there other questions about this example? Any kind of questions?
I have no questions.
Okay. Okay, then let us proceed with continuous random variables like normal random variables. But before we will discuss normal random variables, let us consider the following stuff. Let us consider random variable x that is continuous random variable. With the following density function. So this is 0. This is 1. This is -1. So this is graph of probability density function of x. This is probability density function. First exercise is to find this value. So probability density function is just a function that gives you a distribution of continuous random variable. So the probability for your continuous random variable to get the value inside some segment equals to area under this curve, as you remember. So what is the value of this point?
Well, if it's a density function, then the square under its graph is supposed to be equal to 1, right? And we have a triangle here, and the formula of the square of triangle is 1 divided by 2 multiply the height, right? And by something else, but I don't remember what. By the основание, right? Yes, so, and we need to find the height here. So we need just to solve the following уравнение. My English is perfect today.
Equation.
Yes, yes, equation. Yes, you're correct. So,
divided by 2 multiply h multiplied by 2 is equal to 1. And I cannot solve it in my mind. Yeah, so it's 1.
So h is 1, yeah.
This is just an area of triangle. Yes, and it follows immediately that h equals to 1. So this value is 1. Okay. So we have this probability density function. Okay. Now let us consider a new random variable. Random variable y that depend on parameter theta, and it equals to x plus theta. And now assume that I have assume that we have a sample with only one element. Like y1 equals to 3. And we assume that y1 is distributed according to random variable x, not x, but y. Now, again, we have a likelihood function. But now, because we work with continuous random variable, it does not make sense to ask what is the probability to get this particular value, because the probability to get this value equals to 0 exactly. Because for continuous random variable, the probability to get some fixed value of this random variable is equals to 0 in any case. But in this case, likelihood is the value of probability density for getting our value. Probability density to get the data that we have for particular value of theta. Now I want you to find maximum likelihood estimate for theta. So to do so, we have to understand how a probability density function of this random variable depends on theta. So what happens if I change theta? What can I say about probability density function of this function y theta? So if we cannot just immediately answer this question, we can start with a simpler question. Find or better draw PDF probability density function for example, for theta equals to 1. So this is our first exercise. What happens with probability density function if I add a constant to my random variable?
Don't we say that all the values just become bigger?
Yes, but what happens with this graph?
It should rise.
Rise?
No?
It cannot rise because area under this curve is fixed and it should be equal to 1. So note that
it shifts.
Shifts to which direction? For example, if theta
right?
equals to 1.
Yeah.
Yes, if theta equals to 1, then everything shifts one unit to the right. Indeed. So if we initially have x, and we have y, y1, for example. Then we know that this y1 equals to x plus 1. And it means that, for example, it means that probability, let us consider some segment. For example, this segment. Assume that this segment from A to B. Then probability that y1 is inside segment from A to B. How to express this probability in terms of x? So I ask the question, what is the probability for my value y1, to be inside this segment? And to answer this question, I want to answer this question in terms of distribution of x. So I want to restate this question in terms of x. So if y1 is inside of this segment, what can I say about x?
shouldn't it be outside this segment? So something like a minus 1 and b minus 1.
Exactly. Yes. If x inside this segment, then x plus 1 inside this segment, because this is just a shifted version of this segment, and if x is inside this segment, so I just shift it 1. Shift it like this. So this is a minus 1, this is b minus 1. And I just say that if x is here, then y1, that is x plus 1, is here. And we know that this probability is given by this it is given by this area. And it means that if I want here to get the same area, I have just to draw the same curve, but shifted by 1 position to the right. So I have this curve like this one. In this case, for any segment like this, we will have the same area here and here, just because the whole picture is shifted. So this PDF. So PDF y1 is PDF x shifted by 1 position to the right. Now we can return to our question. We have some specific value of y1, and I ask you to find maximum likelihood estimate for theta for this model.
It's 1.
Why? Okay, if theta equals to 1, what can you say about probability density for this data? What is the value of probability density in point theta equals to 1? If theta equals to 1, then we have a graph like this. This is a shifted version of this graph to 1 position to the right. And we have a particular data point which equals to 3.
Oh, yeah, I see. So it should also be 3?
Yes. So if I have this data point here, this is 3, and then my likelihood for this value of 3, my likelihood is just 0. But I want this likelihood to be as large as possible. How to do it? So in a sense, the problem is the following. I have this graph, and I can shift it to the right or to the left by choosing of this theta. And I want to shift it in such a way that my likelihood for this data is as large as possible. So I want the value of this function to be as large as possible at 0.3.
Well, we should shift it 2 more points, right? So we should add 2.
If we just add 2, we will get the following graph. If we use theta equals to 2,
oh, we need
then
theta equals 3 then.
Yes, if we choose 2, so this is theta equals to 1. If we choose theta equals to 2, we will get a graph like this. And again, likelihood here is just 0. So what is the optimal value of theta?
Theta equals 3.
Exactly. Theta equals 3. In this case, we will have the following graph. So we have this density, and we have this value of my data. In this case, my sample is just one element, so it's just 1 point on this axis, and I don't have to multiply anything by anything. I just find value of my density function at this particular point. So again, this is a similar story. We have our model, and in this model we have parameter. In this case, our model is very simple. It says that our data is generated by some random variable with this distribution. And in this model, we have a parameter that allows one to shift this distribution to the left and to the right. And for a particular data point, we find the parameter, the value of this parameter, such that our distribution, the value of our probability density function that corresponds to our data is maximal. So we say that this value gives us the best fitting for our model. Are there questions about this problem?
I have no questions.
Okay. Then let me consider something more complex. Well, let me assume that we have a random variable x. Okay. Let me assume that I have x1 and so on xn that are normally distributed with some parameter mu and parameter sigma squared equals to 1. So let me recall that probability density function of this normal distribution is something strange. This is our function. And now assume that I have some values like, okay, let us consider again, just two values. And I want you to find likelihood. So we have n equals to 2. Find likelihood function for this data. And find ML year estimate, ML year formula. So now formulas will be much more complicated, but basically it is the same thing as we discussed previously. We just need to find likelihood function for this particular data, and then maximize it. But let us do it step by step. Let us first find likelihood function.
So we just multiply the formula for PDF, putting x there.
Yes, yes.
But
again, you believe again, we believe that these values are independent.
Yeah.
So to find likelihood, we have to multiply the corresponding values of probability density function.
But we don't know mu and sigma.
We don't
we know
need to
sigma.
know them.
I fixed sigma. Let us assume that sigma is just 1, and mu is a parameter that you want to estimate. So your likelihood function will depend on mu. Like previously, our likelihood function depended on theta or on p. So this is the same thing. We know this x, and we don't know mu. So we want to find likelihood function, which will be function of mu.
And are we really going to patience for all
It's a nice question.
Yes, we're really going to multiply two exponentials.
No, please.
Well, it won't be that bad because we just simply add one to another. Yeah.
Yeah, but then we will have to get a derivation of all it. But with the exponential.
But see, when we
Okay.
need to find the maximum, we don't really need to calculate these numbers.
Got it.
Yes, let us do it step by step. First of all, let us just please write down the formula for this thing, and don't be scared before it is needed.
It would be 1 divided by 2p.
Squared.
No. See, we have a square root
Yeah.
under the division sign, but we take this 2 times. So, yeah. So this would be 1 divided by root multiplied by 1 divided by root. So it would be just 1 divided by the data under the root. So it would be 1 divided by 2 multiplied by p, and all this multiplied by exp.
Yes, what is under the exp?
The sum for, so it would be like
2 minus mu squared divided by 2 and minus 5.
5 minus mu squared.
Yes.
So we just need to find.
This seems to be very reasonable. So we find probability density function at point 2 and multiply it by probability density function at point 5.
Yeah.
And indeed, this is just, so we have two terms like this. Okay, we use sigma to be 1, so I will omit it. So I have just 2 pi here. Exponential function. So our x in this formula is this thing, is this value. So I will put here 2 minus mu squared over 2 sigma squared. Okay, sigma is 1, so just 2. And I multiply it by the same thing. And then I will rearrange terms. I have 2 terms. This term and this term. And when I multiply them, it is just this thing, because this square root and this square root and the product gives me 2 pi. And then I will use this formula to multiply this thing and this thing. So this is just e to the power minus 2 minus mu squared plus minus 5 minus mu squared over 2. And
so
I
we
can
just have the quadratic equation.
And I have the following thing. Let me move minus 1/2 here. And I have just this thing. This is my likelihood function. Are there any questions about this derivation? It was scary at first glance, but does it look scary still?
Why have we lost sigma?
Because I said from the beginning that in my model, I assume that sigma is 1.
Thank you.
Just to simplify this model, it is possible to consider model with arbitrary sigma, and actually the answer will be the same for the question that I'm asking, but just to simplify calculations, I put 1.
Okay.
So geometrically, our problem now looks like the following thing. We have this normal distribution, and we choose parameter mu of this normal distribution. It means that we have our bell curve, and we can shift this bell curve to the right or to the left, because the center of this bell curve is mu. And we have 2 points. One point is 5, and another is 2. So we have 2 and 5. And we want to shift this curve in some way such that we have the maximum possible likelihood for these 2 points.
Won't it just be 3.5?
It will. Yes. So any questions about this derivation? This is some algebra, but actually we just use this formula.
But in general, if we need to find the maximum likelihood estimate, we will have to take the derivation, but it's not that scary, because when we will take it 1 divided by 2p, it will be just omitted because it's a constanta.
Constant?
Yeah. And then exponent will be the same, and we will have to just take the logarithm.
But why do we need to find the likelihood function we can just say that, oh, we need to shift the curve between 2 and 5, and the answer would be 3.5.
Well, it is not obvious. Okay, if you have just two observations, well, probably from some symmetry consideration, you can say that it should be somewhere in between. But if you have more observations, like 3 observations like this, it is not obvious how to do it.
Okay.
Okay, so this is our likelihood function, and now I want to maximize it by mu. To maximize this large function, I actually can do the following thing. I can say that this exponential function is monotonic and it is increasing. So the larger value here, the larger value of this exponential function. So in fact, I'm not interested in this exponential function. I'm interested in this thing. So to maximize this thing, I have to minimize this thing. So I want to maximize this. And due to negative sign here, it is the same as to minimize this. Does it look familiar to you? We basically have 2 points, 2 and 5. And we have some point mu. And I want to minimize this thing. Does it look familiar? Where did we meet with something like this? We minimize some of what?
It looks like уравнение окружности.
Уравнение окружности, оно было бы, если бы мы бы сказали, что это константа. А мы хотим ее минимизировать.
We find a minimum of parabola.
Yes, this is also correct. But in general, we already met with formulas like this one, because in this case, we have some point. We have a difference between this point and our data point, and we find square of this difference. And we do the same thing here. So we already met with this kind of problems when we discussed what? Minimization of sum of squares. Linear regression.
Regression.
Can you repeat?
Regression.
Yes, exactly, linear regression. But this is a simplified version. In linear regression, we fitted some straight line, but in this case, we fit just one point, but we do it basically with the same algorithm. We minimize sum of squares of difference between this point and our data points. Then you can actually find the value of mu. Okay, I can just find the derivative, for example, or you can just expand everything and use the properties of parabola. Probably derivative will be easier. So if I want to find derivative, I have to do something like this. So, okay, if this is f of mu, let me rewrite it in this way. I just simplify it a little bit. This square kill the sign here, so I can write it like 5 minus mu or mu minus 5. It is the same thing. So I will use this form. Then the derivative is like this, and this is 2 mu minus 7. And I want to find such value of mu such that the derivative equals to 0. So mu.
3.5.
Yes, it is 3.5. This is actually what is natural to expect, because if we want to minimize this sum of squares, we have to put this mu in the middle of this segment. So I want this mu to be in the middle. And this is actually something natural. I mean that if we have these 2 points, and we believe that these points came from normal distribution, and we want to estimate the expected value of this normal distribution. Well, this is natural that this estimate is just an arithmetic average of these 2 numbers, 3.5. This is just 5 plus 2 over 2. But again, we obtained this estimate using the same idea. The idea that we have model, we have some data, and we find parameters of this model that corresponds to this data to the best possible in the best possible way. So in a sense, we find best fit of our model to our data. So this is a general approach, which is called maximum likelihood estimation. Note that we didn't discuss Bayesian methods that were announced so far. Actually, this maximum likelihood estimation is, well, to discuss Bayesian methods, we have to know what is likelihood. And in a sense, this maximum likelihood estimation will be in opposition to Bayesian estimates that we will discuss on the next lecture. But anyway, to understand what is going on with Bayesian methods, we have to understand this framework. This framework that is related to finding likelihoods and using these likelihoods to estimate of my parameters. So in reality, people use much more complex models that we discussed today. But I just wanted to keep all calculations and all derivations as simple as possible. I tried to find explicitly find the most simple examples. But it is not. The main idea is that this method is in a sense universal. When you think about your your experiment or some your phenomena of real world, you can think about them in terms of these probabilistic models. And when you created this probabilistic model, and if you have data, then you can use maximum likelihood estimation to fit your data to fit your model to your data. And this is, in some sense, it is a good way to do it. But on the next lecture, we will discuss, in a sense, even better way to do similar things. So, are there any questions so far? Actually, we already met with maximum likelihood estimation when we discussed logistic regressions and some other methods like logistic regressions with random effects, or even just simple linear regression. They are also maximum likelihood estimators for appropriate probabilistic models. And the main feature is that you can create these probabilistic models just as you wish. And then you can just apply some mathematics to fit them. Okay. If there are no questions, then we probably can finish for today.
Thank you.
Okay.
Thank you very much.
Bye.
Bye.
Спасибо.
До свидания.